In today's video, we are going to be taking a look at what are called periodic trends. And in order for us to take a look at the periodic trends, we need to review a little bit of the history of the periodic table. So a long time ago, there was a Russian scientist named Dmitry Mendeleev. And Mendeleev is credited with being the first person who arranged the periodic table. And when Mendeleev arranged the periodic table, he arranged it based off of atomic mass. And then he further organized it based on reactivity. So when we take a look at the image on the upper left-hand side, we're taking a look at how Mendeleev arranged those elements based off of their atomic mass. And we recognize a lot of the elements that are there already. And what I want you to pay attention to is this first column on the left-hand side. So when we look at that first column, we see similar elements to what we see in our first period of our modern periodic table. So what we did is we actually kind of flipped that first period or first group there that's circled from Mendeleev's table, and we flipped it around to get the image below. And this is really how our periodic table started. So we see some similarities to what we see already. So a lot of the elements in group 1 and those alkali metals look very similar. The alkaline earth metals look really similar. We see some of our halogens with fluorine and chlorine. But what do we not see? What family is missing? What do you think? So the family that's missing is actually going to be the noble gases. And the noble gases are missing because they don't react. Because remember, we learned during electron configuration that they are super stable. And so if they're not reacting, it's not possible for Mendeleev to have discovered them because he organized the elements based off of reactivity. So they hadn't been discovered yet because they do not react. So while our periodic table does still show some trends in increasing atomic mass, right now our periodic table is actually arranged based off of a different property. And Henry Moseley, the guy that's pictured over on the left-hand side of the screen, was the scientist who helped us rearrange the periodic table, and now it is based off of atomic number. And remember, atomic number is the same thing as the number of protons in an element. And Moseley arranged it based off of atomic number by using X-ray spectroscopy just to determine how many protons were in each element. And what's really amazing is that Henry Moseley joined the British Army in World War I, and he was actually killed at the age of 28, which is super young. And so we always question, what could Moseley have contributed to science had he lived longer? Because right now he is the one who's attributed with having arranged our periodic table the way we still continue to use it to this day. Now that we've reviewed a little bit more about the history of the periodic table, let's actually talk about periodicity, also known as periodic law. They are the same thing. Periodicity or periodic law are when we see a variation that is regular. So when we see a regular variation in both, and this is the key word here, in both groups, which remember are the columns, and periods, which are the rows. So what we're going to be looking at in the rest of this video are a couple of different periodic trends that we're seeing, and then we'll actually continue with more periodic trends in our next video. So the first trend that we're going to be looking at is what we call electron shielding. And in order to understand electron shielding, we need to first remember the difference between core and valence electrons. So remember, valence electrons are electrons in the outermost shell, or the outermost sublevel. Same thing. core electrons are the electrons in the inner shells, or inner sublevels. So what we need to remember is, or what we need to understand about shielding, is that the electrons are negatively charged and the nucleus is positively charged. So the electrons that are in the cloud are going to be attracted to the nucleus. But the outer electrons, our valence electrons, are going to have a harder time getting to the nucleus because of the inner electrons that we see. So because the electrons are both negatively charged, these electrons are going to end up repelling one another. So the core electrons are going to be trying to get to repel the valence electrons from getting to the nucleus. So let's look at the first trend. We're looking at shielding within a group. So within a group, shielding is going to increase as we go down a group because of the increased number of core electrons. So as we go down the group, right, we're increasing atomic number, which means we're increasing protons, but we're also increasing the electrons, and we're adding in more energy levels. So as we're going down that group, we're adding in more core electrons, which means that the shielding of the valence electrons to the nucleus is going to increase, which means that those valence electrons are going to have a harder time getting to the nucleus. Now, when we think about shielding within a period, we're going to say that that shielding is actually minimal, so it doesn't really happen, or doesn't really change, because the number of core electrons doesn't change. So if the number of core electrons isn't changing, then the repulsion between the valence electrons and the core electrons isn't really happening. So then the shielding itself is very minimal because those core electrons aren't changing. And an example of this, where we can look at this, is going to be looking at the elements lithium and cesium. So the electron configuration for lithium, just a little bit of a review, remember, is 1s2, 2s1. And for cesium, we're going to go ahead and use the shorthand notation, where it has the core electrons of xenon with 6s1 as its next sublevel that it fills that xenon does not fill. So when we look at these, the number of valence electrons is staying the same within that group. However, the number of core electrons is going from 2 to a number much higher than 2. And so since we're increasing the number of core electrons, we're increasing the shielding down that group, even because lithium and cesium are both in group 1. And remember, again, shielding is that idea that the core electrons are blocking or shielding the valence electrons from getting to the nucleus. So the next trend we're going to be looking at is that of atomic radius. So atomic radius is going to be the distance from the nucleus of an atom to the outermost shell, or to the valence electrons. And this overall trend is going to look like this in the periodic table. We are going to end up increasing as we go down a group and decreasing as we go across a period. And what we're going to be talking about is why do we see those trends that we do. So looking at the first question, why does the trend increase down a group? Well, it's increasing down a group because we've added in more core electrons, and therefore we've increased the shielding that we talked about on the last slide. But we've also added in more energy levels. So those atoms are going to have to get bigger in order to accompany or accommodate all of those extra energy levels and core electrons that we're adding in. So if the atom's getting bigger, then the radius is also going to get bigger. So the next question we're going to be looking at is, why does the trend we see decrease as we go across the period? And the reason for that also relates back to shielding. As we're going across the period, remember, we are adding in more valence electrons. And as we're adding in more valence electrons, we're not really changing the core electrons. So the outermost electrons, or the outermost shell, starts to be able to overcome some of the shielding that's coming from those core electrons. As I add more valence electrons to that outermost shell, those extra valence electrons are going to kind of be able to overcome the core electrons and actually draw in closer to the nucleus. This is why we see that atomic radius is going to decrease across the period, because that outer shell is going to be coming in closer to the nucleus. So the last thing we're going to be looking at today is how ions radii change based off of whether they are a cation or an anion. Remember, cations are positively charged ions, anions are negatively charged ions. So when we're looking at cations, we're going to look at them first. We see our regular sodium ion on the left-hand side, and that sodium ion is going to lose an electron, which is what this arrow is showing us. And as it loses that electron, we then have the sodium ion with a +1 charge. So how could we describe what happens between the sodium atom and the sodium ion? Well, the atom is bigger than the ion. The ion is going to get smaller. And here's why that atom is going to get smaller. So in the sodium atom, we have 10 core electrons, and we have 1 valence electron. But in the sodium ion, we have 2 core electrons and 8 valence electrons, which I'm going to abbreviate to VAL. So those valence electrons that we have in the sodium ion are going to be able to overcome the 2 core electrons it has, which means that outer shell is going to end up getting closer to the nucleus. The other thing is, when we form cations, remember, we're actually losing energy levels. So we lose electrons, thereby losing energy levels. And if we're losing those energy levels, innately the atom has to get smaller. So now let's take a look down at the bottom at our anions. So when we add in, so we're looking at a chlorine atom versus a chlorine ion, and here we're gaining an electron. The chlorine atom is gaining an electron to make it the chlorine ion. So when we add in an electron, so adding in extra electrons without adding in extra protons, because remember, we're not changing the element at all, so we're not changing the number of protons, causes the added electrons, or the extra electrons, or electron, causes the added electrons to start to repel one another. And if they're repelling each other, because remember they have the same charges, they're both negative, if they're repelling one another, they're going to innately be taking up more space, which is why we see that anion ions, so atoms that form anions, actually are going to have a larger radius when they form that ion, because those electrons are going to be repelling one another, therefore taking up more space. And that is it for shielding, atomic radius, and ionic radius. And in the next video, we will cover a couple of other periodic trends.